Good morning, everyone. And welcome to today's webinar hosted by Yokogawa, Europe. We will show you how the unique capabilities of a ScopeCorder can solve your complex measurement applications. Before we go further, I want to review the functionality of WebEx platform that we use today. I have everyone on mute, as you might have already noticed, to avoid background noises that may distract you from listening to the webinar. Throughout the presentation, I will be managing the chat functionality. So if you have questions or comments during the webinar, you can enter those in the question or chat box throughout the presentation. So back to today's webinar, I will now pass you over to Clive Davis, our marketing manager here in Yokogawa, Europe, who has been solving customers' measurement challenges with ScopeCorders since before their introduction in 1997.
Thank you very much, Nora. ScopeCorders. So we are describing it as more than a test tool. When we created this name back in 1997, it was a lot less capable than it is today. It can be seen more as in some terms as a conceptual product because it is modular and it has a wide variety of configurations and capabilities. That basically means that it only becomes a solution for your measuring application when you've equipped it with the relevant modules and options. That essentially does present a challenge to us and in order to basically convey the capabilities of an instrument to the customer. So the objective of today's webinar is to give you a flavor of the capabilities of the product and inspire you to consider to use it for your complex measurement tasks. What this webinar will endeavor to explain will be how we actually use a lot of data. But first and foremost, it's not just necessary to capture data, it's actually to use it in a way that will give you meaningful information. So that, of course, will lead on to the types of analysis and other capabilities of the product and how easy it is to actually do anything with the data. We will be focusing on the isolation technology because unlike normal oscilloscopes, of course, we offer high levels of isolation and high resolution isolation. As I mentioned, we will also be talking about the extensive measurement analysis tools, how we actually offer specific and unique capabilities if you're involved in automotive and railway applications, how we actually also offer the capabilities of long-term recording and the ability to capture fast-moving events as well, using our dual capture capability and our history functionality. And we'll also describe to you what tools are available for using the data outside of ScopeCorder. Obviously, we are offering this as a standalone solution, as a very intuitive and easy-to-use solution for measurement applications. But of course, users will also like to use the data and their own existing analysis tools for maybe presenting the data in different ways. So, trying to answer the question, what is a ScopeCorder? Well, as we say here, it's a configurable application solver. We are now offering a range of 2 or 3, if you consider the DL350 as 2 instruments. We've recently introduced the DL350, which is essentially a portable version, or more portable version, with a rechargeable battery pack, which offers essentially a lot of the, or most of the functionality of its larger brother, the DL850E and the DL850EV. And I'll explain those differences as we go along. Yes, as you might feel, the name ScopeCorder was created originally because it does combine the features of an oscilloscope and a high-performance data acquisition recorder, and hence the name ScopeCorder. Of course, that only basically is a name. It doesn't go into describing what the instrument can actually do. We can do this and use it for long periods of time. There is a little difference between the capabilities of the 2 products in terms of performance and how long they can measure for. We will be discussing that as we go along. And of course, it is a standalone instrument, so you do not need to connect a PC to it in order to use it. Although, as we mentioned, we can use software tools and the connectivity of the product to take the data out in a way that you can use and you wish to use. First and foremost, it's a configurable instrument. So that means that we can install different types of module in it, depending on the task that you want to use it for. As you can see here from the range of instruments, or some of them, range of modules, or some of them here, there are different types of connectors, different numbers of channels associated with these. What this means in practice is we can handle voltages up to 1,000 volts of isolation in this case. We can now also handle, through the portable version, Cat 2 and Cat 3 safety, electrical safety standards in order when you're using it in a portable format. More modules we have will handle things like temperature, vibration, acceleration, strain, and frequency. We also have logic modules as well, which means, of course, you can compare analog signals alongside digital ones. We also now introduce some of the modules which are usable if you're working in an automotive environment, whereby we can also monitor those bus signals alongside the analog waveforms, and we'll talk about that a little bit later during this webinar. If you need more channels, and we'll talk about the total number of channel counts as we go along, we can also introduce scanner modules. Most of the modules that we provide are simultaneous sampling, because of course that means that you are capturing all the details time synchronized. But if you need to do longer term testing and to do many more channels, you can also mix and match with 16 channel voltage and temperature scanner modules. So these are very configurable in this respect. Okay, so we can address, how long can I use a ScopeCorder for? And we talk about milliseconds to months, and what you can do with this longer memory. So essentially, three things you can do with longer memory in a waveform acquisition instrument. We can sample faster, which basically means you get better time resolution. Or we can do longer measurement times. So of course, more memory, same sample rate, we can save for longer periods of time. Or we can use more input channels. And of course, that's where if we've got maximum numbers of memory, we can then use that to share across the number of available channels, which is one way that we actually describe the memory handling within a ScopeCorder. Because of its flexibility, it's hard to actually describe it in terms of memory per channel, so we actually do it in terms of overall memory sizes and then split that up between input channels, for example. So what does that mean in practice for our different models of ScopeCorder? Well, here you can see for the DL850 and the DL850 EV, essentially there's no difference between the DL850E and the DL850 EV, apart from the fact that the EV, which is the vehicle edition, can accept the serial bus modules, like the CAN, the LIN, and the SENT modules. And you will see here, for instance, that we have got, just a pointer here. You can see here that we have 8 modules here. That essentially is the capability of the DL850, that we can install 8 different modules within the unit. And you can see here that these are 2-channel modules, and here we have 4-channel modules. So that starts now to give you an idea of how we use the configuration, and hence the table down the bottom here of the built-in memory, which we can expand up to 2 gigapoints. How that would actually mean in terms of how long we can sample for. So, for example, if you install 8 100 megasample per second modules, which are also 12-bit modules, which will also handle 1,000 volts. We can, with the 2 gig of memory for 16 channels, which is the maximum you can install for 100 meg, you would get that for 1 second. And you can see, of course, that we have 4-channel module, which has the capability of 1 meg sampling. It's a 16-bit module, and so that means that we can install up to 32 channels of that. And so with 32 channels, 1 megasample per second, we can sample for 50 seconds. So that's giving you an idea of how the memory size is achieved in practice. However, with the DL350, we can also save to internal hard disk or external hard disk using an eSATA interface. That means there is a restriction on the speed because it won't work as fast as the internal memory can work. But in this case, we have 1 megasample per second. If we have 1 channel, we can run that for 10 hours. And you can see that when we sample as low as 1 kilosample per second, we can sample 1 channel for 200 days. Hence, that is the specification we publish within our brochures. And with this proprietary, we'll talk a little bit about shortly of how we handle that amount of data, because as you can imagine, it takes quite a large amount of mathematical processing to actually use that data and use it in a fast enough way to actually enable the user to work efficiently. The other instrument we have recently introduced is our portable version, the DL350. This has less memory, but it still has 100 megapoints of internal memory, and we can also save directly in real time to SD card inside the machine. So as we can see here, in this case, we have the ability to install 2 modules within the DL350, and with a 4-channel module in both slots, it means that we can have 8 channels, and if you have a 2-channel 100 megasample per second module in both slots, it means we can have 4 channels of that. So in practice, with the 100 megapoint memory per slot in this case, we can sample at 100 megasamples per second, 4 channels for half a second. And then, as you can see here, if we have 8 channels with using the 4-channel module here, we can sample 1 meg and do that for 20 seconds. Like the DL850, we can also then save directly to SD card. So what this means in practice, if you have very, very long duration tests, durability testing, when you're sampling as low as 1 kilosample per second, we can save 1 channel for 50 days. Or if you're going to sample a little slower, we can do that down to 50 days. And so you can see, therefore, that also is the published specification. For 8-channel recording, we can save for 50 days and be sampling data at 100 samples per second. And this will be, and this can be 16-bit resolution. The other thing we can do is essentially use the memory in a different way. So if you choose shorter memory lengths to capture, the history memory is then essentially active. What the history memory does, and this is a feature that we've been offering on all our ScopeCorders and oscilloscopes since we introduced them back in the late 80s, is that we basically split the available acquisition memory up, and it will save automatically each successive triggered acquisition. This means that they are all available to you in memory without having to do anything else, up to the maximum number of history memories that are available, which depends on the maximum memory that's installed in the ScopeCorder and the memory length that you've chosen for your particular test. So this means that we can save the abnormal waveforms without necessarily having to be too careful about the trigger conditions we set it up for. So, for instance, if you do not know precisely what your abnormal waveforms look like, therefore you can't set up a trigger just to capture those abnormal waveforms, it means that they will be saved within the history memory, and then you can use the ability to go through those history memories and find what those abnormal waveforms look like, and potentially then set up your triggers on those particular waveforms to capture just the abnormal ones you're looking for. So within a DL850, which is the larger laboratory version of our ScopeCorder, we can have up to 5,000 history memories. In the DL350, we can have up to 1,000, because essentially the maximum memory is less. And as we described, we can then isolate individual waveform records from the history to do the further analysis. How that looks like on the screen is shown here, for instance. So here you've got 4 individual histories, which in this case is just showing a different frequency of a sine wave, and what they will look like if you decide to superimpose those on screen will be, as you see here, the sort of image you might expect. We can, of course, look at individual waveforms, and we'll also be describing a way shortly of how you can use the analysis and statistical measurement features of a ScopeCorder to do some statistical measurements of the data in your history memory. So I mentioned that we were going to talk a little bit about isolation and how this differs it from a normal oscilloscope, which is ground referenced, which means it can't handle automatically multi-phase measurements, for example, without dangerous practice of the oscilloscope. And here on this slide, you will see a picture, and this picture happens to be the inside of one of our modules, our 100 megasample per second module, 12-bit, 1,000 volts of isolation, highlighting the fiber optic isolation within the module. Essentially, what the isolation, the reason why we stress the importance of the isolation is what the requirements for a user are. First of all, is to offer high levels of precision. Of course, precision in this case means how fine detail I can look at in terms of vertical amplitude, which is characterized by the resolution of my A to D converter. How repeatable are my measurements, but also, of course, how noisy are the signals that appear on the display that are measured. So, of course, in this case, isolation potentially offers low noise measurements as well. Of course, resolution is not, on its own, is not useful without accuracy as well, and they're not necessarily meaning the same thing, because obviously accuracy is how good and how accurate the actual measurement is, not how reproducible or that it happens to be at any one time. So even if you have high resolution, it's not very useful if the go very high either. So obviously, the aim for a measurement instrument manufacturer is to be able to offer both in the same instrument. As I mentioned already, we basically use these techniques and the fiber optic isolation in order to achieve 100 megasamples per second at 12 bits and also provide 1,000 volts of isolation. What does that mean in terms of examples, or how is that actually implemented? Is shown on this slide here. So how we implement that is by doing multiple levels of shielding and isolation. And so what you can see here, for example, is the individual shield around individual circuits. We then have insulation and a shield around the module itself. So we have multiple layers of isolation. And as you can see in this one, it means that not only do we have isolation within the module, but we have high levels of isolation between modules. And that essentially enables us to also achieve high levels of common mode rejection ratio. This chart here you see on screen is essentially showing that with a 1 megasample per second 16-bit module, and in this case we're running at sample rates of 500 kilosamples per second. As we can see here, we are able to achieve 100 dBs of attenuation for noise. What that means in practice, of course, is if you basically are looking at control signals. This is an example. So we're looking at a control signal within an inverter. Therefore, you've got potentially high voltages being on the motor side, on the output of the motor, but we've got lower signal voltages, and we want to basically look at the gate signals as well. So we're using a probe to probe the gates, an isolation probe in this case, and therefore we can see that there is no noise appearing from the motor side, or the output of the motor, through to the much lower voltage gate signals. So that, of course, is an immediate result of low noise and high levels of common mode rejection. Also, we are moving, of course, ever and ever to faster speeds, and this shows an example of, or then a probe which is showing the outputs from of the motor. And what you might see in this case is this type of typical pulse width modulation motor driving waveform. We don't see any difference. These waveforms potentially will look very similar to each other. But of course, we highlight the advantage of sampling at high speed. And of course, this is essentially the virtue and the need to sample at high speeds. So essentially, the story here, of course, that it's not only necessary to sample at high speed or at high resolution or with high levels of isolation voltage, but you need to do all three simultaneously, and that essentially is what our high speed module provides for you. In this case, we can't see the overshoots if we're only sampling at 10 megasamples per second. So the all-important question is, okay, so you've convinced me that we can capture data, we can capture large amounts of data, but of course that from an objective is not sufficient. I want to be able to gain meaningful information from that data, and we potentially have a large amount of it. So what can I do with that? Well, first of all, we have data which can take over a very long time scale. And so what we are offering here is the ability to look at up to 2 billion samples of data and basically find the bits you're looking for very, very quickly, or in the blink of an eye. We implement this in the DL350, which is the instrument which can handle up to 2 billion samples of data, using a tool called GigaZoom Engine 2. What this means is that using the GigaZoom Engine 2, we've got 2 zoom windows. You see here, for instance, that we've got a large amount of data on screen. So it can be over an extensive period of time. We want to look at the parts of this in detail. So we can basically expand one part like this, and we can expand the second part. So by providing 2 zoom windows in this way, we can do more than one thing. We can look at the cause and effect of something. So something which has happened at a very early stage, we can then track a long way forward and zoom in on both those separate parts. And as you will see, using the other tools, the measurement tools we will be describing, we can then make measurements between those 2 points and accurately determine and look at cause and effect between channels. Something happens on one channel to cause and effect some seconds, maybe even minutes or hours later somewhere else. So we can do precise measurements between those 2 occurrences. Or we can look at send and receive, very early stage of selling this type of product. We're looking at using it for sonar applications, for example, where we were looking at both the transmission through the water, the signal being transmitted, and the reflection, and we could therefore look at the timings between those and look at the pulse shapes of those. And it also means we can do zoom in zoom, because there's no restriction over where you put these zoom windows, so they can essentially be sitting over the same part of the waveform. it is seamless, very quick in operation, and very intuitive. With the DL850, we have dedicated controls for controlling the zooming on the DL850, and in the new DL350, using the touch screen, it's just essentially touch the screen, brings up a menu, and then you can turn on the zoom window and then use your fingers to find the parts you're looking for. What can you do with that? What can you now do? Because now, so we've zoomed in on the portion of the waveform we're looking for. Well, you can ask the machine to work in one of two ways. You can ask it to do, you can actually drive cursors and position them yourself, or you can ask the machine to do automatic measurements for you. So with cursor measurements, as you might expect, we have the ability to have a different range of cursors. What you see on the display we have here is a view of the new DL350. And on the top part of the display, you can see the original waveform up here. Down the bottom, the lower part is a zoom picture. And you can see here, the window around this part is the extent of the zoom. So using the touch screen in this case, I can move and scroll the position of that zoom window. So you can see here that I've got two cursors shown. In this case, it is horizontal and vertical cursors. And so by positioning those on the edges of the waveform, in this case, down the bottom here, I can see the measurements of those two cursors. So these are, if you like, standard oscilloscope type cursor measurements. We've also then got, interestingly, markers which follow the waveform. So rather than position these completely by hand, you would select which waveform to sit these markers on. So in this case, we have one waveform with two markers sitting on the same waveform. And we then basically move these and they follow the waveforms you've chosen. These can, of course, be different waveforms. So this means that you're timing of edges between waveforms using manual cursors. We can, of course, using the automatic measurements, which I'll talking to you about shortly, is ask the machine to do that automatically for you without positioning the markers themselves. But it's just a way to run these manually without having necessarily to go into the automatic measurements mode, which we'll now talk about. So with automatic parameter measurement mode, this allows you to put on screen and ask the machine to do all these measurements for you. And essentially what you do is set two cursors around the portion or around the number of waveforms you want to look at, and it will do these measurements on screen. So you can see here on this view that we've got peak to peak shown and a frequency ticked for one channel. How that will look in practice is like this, although actually I'm also now showing you another capability of the product, and that is not only can we show the automatic measurements of the waveforms. So we've got our start cursors here and we've got our end cursor here, and we're essentially asking the machine to calculate the peak-to-peak of the waveform between those cursors. So it means that you can choose the part of the waveform you want to do these measurements over. And also then we've got the frequency measurements as well. By turning on statistics, as we have done here, what it means is for continuous acquisitions using the trigger, we will do statistical analysis of that measurement. So we will see how those measurements vary over time over my waveform for continuous waveform acquisition. So you can use it as a real-time tool, effectively, to see how continuous acquisitions vary. Or we can do it over different things. So using continuous, it will do this over successive triggers, or we can use what we call cycle statistics. And this essentially means that if you have one acquisition, on screen, and it could be, of course, a lot of waveforms which would not be necessarily zoomed in like we see here. We can also do the statistical measurements over the complete screen full of waveforms, or we can do it through the history memory. So I described how we use the history memory to look at and keep in memory successive acquisitions, successive triggered acquisitions. Well, we can also apply statistics to those as well. So it means that using history statistics, we can actually therefore look at how the waveforms vary through time. And of course, those triggers can either be short triggers, very short dead times between them, or they could be something over minutes and days or months. So essentially that data will be kept in memory, and you're able to use the measurement features and statistics to analyze that long-term data as well. We'll now move on a little bit just to talk about how we are providing the products, particularly for supporting vehicle applications or railway applications. The reason we did that, we were the first company to offer seribus analysis on our digital oscilloscopes. Essentially, that enables the user to probe physical layers of buses like CAN, LIN, or even I2C or SPI, in order to look at the physical behavior of those buses. Well, in a ScopeCorder, we do it slightly differently. In a ScopeCorder, it is basically implementing a node of those buses within the module, which essentially means it's acting like it is part of the bus, and therefore looking at the performance of the bus. And it's basically monitoring and decoding those channels. What this means is that we can look at simultaneously an input into a ScopeCorder electrical signals or physical signals, which are of course driven from sensors, whether it be pressure, temperature, or whatever it happens to be. So we're looking at those physical sensors, and we're also now looking at the output effectively of the powertrain management system. This basically means that you can use the one product to categorize the whole electrical system and look at the latency or delays in the system, and allow the engineer to optimize those and see where the issues actually lie by comparing what the sensors are showing and how long it takes, or what happens with the outputs of the seribus monitors. And we can therefore do holistic testing over the whole vehicle with the one instrument. And of course, now we can do that with a portable product as well. It means that it is much easier, therefore, to do tests in the field and easily, and do real world test conditions. So we do decode the CAN, LIN, or CentBus signals. We basically then can trend these as analog waveforms. This particular example shows simulations of 4 of the signals from a CAN bus. We can show up to 60 signals from a CAN bus per channel, and a CAN bus module can be connected to two different CAN buses. So we can do multiple buses as well. And we also provide tools to help those people who are familiar with this technology to choose which signals they want to use within ScopeCorder. We do this with a small software tool which we supply free of charge, and which is downloadable from our website. And essentially, we take in CAN example is the CAN DBC file, which will essentially describe every signal which happens to be in the CAN bus, which has also been generated during the development process of the CAN bus. We can then very quickly choose which signals to implement and export those and import those into the ScopeCorder. This means it's very quick to do. It doesn't mean you can't do it on the front panel of the ScopeCorder. It's just that, of course, you need to know precisely the ID, the CAN ID of the signals, where the data, how long the data is, and where the data lies within within the data frame. So this is just a quicker way to achieve that in practice. We also now will be offering GPS, which essentially will help the mobile testing, the drive testing. We have one issue at the moment with the GPS sensor for our new portable DL350, which means it still needs to be tested for the latest European Union radio frequency directive, which now applies to both receivers and transmitters. But when we are able to offer that, it means that we will be able to do much more complete drive testing using the features which I've just been talking about, but of course now getting both position and timing information in the data file as well. So that means that we can do this for mobile testing, but also if you're using instruments in more than one place, because of course if we're using GPS timing, for example, it means we can synchronize measurements which can be separated by meters or hundreds of kilometers, because then the test data themselves will be synchronized. And that is also a feature which we provide on our DL850 larger system as well, to do that GPS time synchronization, for example. Let's talk a little bit now about some specific features which apply to the bench instrument, the DL850E and DL850EV, which basically means that if you're using it for very long-term durability testing, this can be dangerous if you're also looking for what happens over very short periods of time. Because traditionally, to test for very long periods of time, you have to sample for slower sample rates in order to be able to capture all the data you're looking for. The danger, of course, by doing that is that you will miss the detail of high-speed events. Well, that is solved in a DL850. And this image showing how that works in practice is we have that low sample rate trend, but we have a very much higher speed event which comes along. We've implemented that, and we actually solve that using the dual capture capability. Well, how does that work? Well, let me just change my pointer here to a highlights. So what you've got here, for instance, is the main screen of our DL850, and this is showing the slow sample rate. And you can see that slow sample rate because we show here it's 200 meters per second. With the dual capture, it's using a different system. It's also using a different trigger mechanism. So we can set up our sample rate for our high-speed events separate to our long-term durability testing, and set up one of the extensive range of triggers in order to trigger on those abnormal events. And so what you can see here is at a normal event, and then actually we only see one in the window. If we saw more than one in the window, one of those would actually be highlighted with a little arrow we've got, which we have here. And if we do that, you can see on this lower screen, which is a zoom image, if you like, of both of them, they've merged them together. So we can now see them actually at the same time. So this is how we actually knit the information from our high-speed events using the dual capture together with the long-term information which we have here in this case. So, and we can, as we described, it is possible to have up to 5,000 saved within the DL850E or DL850EV, which of course does make it ideal for this sort of testing. And now, of course, you can have a high-speed signal, a high-speed module installed, 100 megasamples per second, but actually normal purposes running very, very slow sample rates and saving that data to the memory. So we're not going to miss anything. going to talk a little bit more now about some of the more extensive capabilities of a ScopeCorder or a DL350, and that is real-time maths. We're now moving into an area where without you need a sort of appreciation of the overall capability of the real-time maths to really be able to apply it to your particular application. That can be a little difficult to understand because it's not until we are presented with a requirement from users where they say, I want to do this, this and this, I haven't found an instrument which will do that. That will then start us thinking, yes, we can use a combination of capabilities of a product. In this case, it could be real-time maths to achieve the sort of effect or results that the user or you can be looking for. So what I can only do today is give you a flavor of that capability. And give you a couple of examples of where real-time maths will achieve the measurement or the capability that the user is looking for. Essentially what happens is maths operations are performed in real time. This is done before that data is put into the acquisition memory. There can be a small time delay, of course, because real time is as much a concept than practicality. So there can be a small delay in practice. But to all intents and purposes, it will appear before while the acquisition is in progress. The other additional benefit of doing this real time is we can also trigger on the output of those real time maths channels, which basically means that for some very, very strange signals where you can't even use the enormous ability of the triggering capability in a ScopeCorder, which we're not going to include in today's, particularly in today's webinar, we can also trigger on the output of real-time maths channels. The maths is performed at a high speed, 10 megasamples per second, and we can also use real-time maths in what we've just described as your capture mode. So I'm not going to spend a lot of time going through the different types of real-time maths, but I just want to give you a flavor of the extent of the ability to do this, and I will just use a couple of these as examples to give you an idea of the capabilities. So we've got differentiation, integration, we can do rotary measurements on encoders, for instance, we can do digital to analog conversions, we do polynomials, we can do real-time RMS using maths if you're not using an RMS module in order to do RMS calculations on waveforms. We can do power measurements where we can also show active power, reactive power and integrated power, logarithms, square roots, trigonometric functions, electrical angle, taking torque measurements, do pulse modulation, etc., etc., etc. And we also have a couple of ones which are unique to the DL350 EB, which means we can also trigger on CAN IDs from standard analog modules, not using the CAN modules themselves, in order to trigger our acquisition, for example. So I'll give you a couple of examples of this. A nice easy one, actually, is this one. It is just using a very, very simple operator. In this case, we're just dividing one channel by another. But in this case, we're using this as a sort of automotive application where we have a continuous variable transmission. Two pulleys connected by a belt. Normally they're running at the same speed, so you would expect if you were doing a division, you'd have no output. If one of these belts slips, of course, then as you can see on the lower picture down here, there will be a shift, and the net result of that will be a pulse which you can trigger on. So we can now trigger on the different signal and just acquire data during that period. So that's just quite a simple example, but it's a practical one. Another actually more interesting example is using differentiation. Differentiation, of course, means that we're not looking at the voltage amplitude of a signal, we're looking at how fast the amplitude is changing. And in practice, with normal types of oscilloscope trigger, as we can see down here, we have potentially very small changes in amplitude, which are always difficult to set triggers on. However, with the differentiation, if we differentiate that signal, what you will look at in practice, you can't actually see at all the original waveform and what effect it's having on the original waveform. But by differentiating it here, what we have is a rate of change signal now produced, and you can see that the level is just a pulse, which we can now use as a trigger. So that is a practical use of the real-time mass to trigger the instrument, and it means that we can then. The order's gone. Yep, this is the right order. So what we can use this in practice for, and this is showing two examples of that. In this case, it is the first example is the stepper motor for an adaptive front headlight for an automotive application. We're looking at the stepper motor, and we're able to capture just that misstep, and of course then diagnose the effect of that on the system. Because of course we can then also capture the vibrations created from the fault in the stepper motor. And the second application here is showing a biomedical application where again we're using the signal to look at the blood, in this case a blood circulation scanner and a laser, and of course this would potentially cause misalignment in the laser itself. So this is just shows how that could be used in practice, just to give you a flavour of the potential of the real-time maths capability. The other thing we can do with the DL350 is have another option which allows you to do more comprehensive real-time measurements of electrical power. In the standard real-time maths, the G3 option, we're able to trend and look at how power factor changes. With this option, we can actually categorize up to 125 types of electrical power related parameters. So of course this means that using a DL350 EV, what we can do is look at raw waveforms, and we bring in raw waveforms into the DL350. And we're looking at both raw waveforms from the input to the converter and the output from the converter. We can also then calculate the power values related to these, and using a torque sensor input also, and using the real-time maths, we can also bring in the torque values as well. So it is possible to do categorization of a whole inverter using a DL350, using these extra capabilities that we're offering as options on the unit. So one of the things I mentioned we will talk about is what software tools are available. So what I've done so far is touched on the built-in capability of the measurements, and as we've seen, we have extensive measurement capability and to produce, and of course you can export this data as well, both in terms of raw waveform data and images and the actual measurement data as well. So we offer a range of tools in order to support that. Some of which are supporting our own software tools, and some of which are supporting third-party tools. So in terms of our own software tools, we have various flavors of free software. We have essentially a program called XViewer, and as you can see over here, we have an overall XViewer software, which you can download from our website. We have a trial version available for that, which allows you to use full functionality for 30 days. Which essentially it mirrors the functionality that you see within the ScopeCorder itself. So we are able to use the standard cursors and parameter measurement capability, the statistical analysis, and we can also do mathematical functionality in FFT, not only in the ScopeCorder itself, but also within the software tool. We also have a very basic version of that called the XViewer Lite, which just essentially allows you to do zooming, do simple cursor measurements and convert the data to CSV formats within the software tool, because it is possible to export data from the unit in our WDF format, which of course means that the software, the data is in its minimal form. If you want to convert to a CSV, it expands the data, of course, and means the file is much heavier, much bigger, and of course that's easier to do in the PC, although it is possible to export as CSV from the instrument. For the DL350, we also provide, which is, as I mentioned, a new portable version. It does come standard with a very simple software tool. The software tool enables you to export data, but also enables you to take setup files within the DL350, bring them into a PC, modify them, and put them back. So if you want to basically do setup creation in your PC, you can do that very simply using the DL350 assisted software. We then have various other tools for simple monitoring purposes, for remote monitoring and operation, transferring image files. Within our products, we also have web server. Even within the DL350, it has a web server. So if you connect it using the Ethernet interface, we can also see the screen of the DL350 on your PC, and you can press start and stop button to actually start and stop the acquisition. So if you want to use it in a remote area and in your office, you can monitor what's happening on the ScopeCorder remotely on your PC. And we also provide various other software tools which allow you either to use proprietary programs like National Instruments LabVIEW, or use other types of analysis tools and software tools to view and analyze your software in different ways, or a set of sample tools for creating your own software platform if you're a programmer yourself. We also provide MATLAB toolkits, and it is possible to save directly in the ScopeCorder in MATLAB format. So if you use MATLAB, we can save as MATLAB format without connecting the instruments to the PC, and just export in MATLAB formats automatically. For the DL850, it can handle a large amount of data. We do provide what we call an advanced utility option. Basically, this means that you can connect not only to the DL850, you can actually take data out of the machine at the same time it's saving to its own internal data. And if it's for a very long-term test, where you would normally be able to touch the instrument because it's doing continuous testing, what this means is we can then export the data at the same time and use the PC to analyze it while the test is continuing. And that is a function, or an extra function we provide for XViewer, which enables us to do that. So that's just a very quick overview of the software support we provide for this. As I said, most of these tools are available to download from our website. So I just wanted to give a little summary of the differences between the DL350, our new portable unit, and the DL850 EV. With the DL350, we're describing it as having the ability to take laboratory performance, accuracy and precision out into the field, because of course there are many test tools available you can take into the field, but essentially they wouldn't have the levels of precision that you will be using in the laboratory. So we're now offering the DL350 as a tool which will achieve that purpose. What we see here is, of course, a difference in size and weight. The DL350 is a little under half the weight, and it's under half the size of the DL850. So one of the key differences, the reasons for that, is it will accept two modules. We describe the fact that DL350 will therefore be able to do 8 channels of analog in real time using 2 4-channel modules, plus 16 digital, because the mainframe also has 16 digital channels available as well. The DL850 has 8 channels. Sorry, 8 module slots, so it means we can do more channels, but also a different mix of channels. So it means that if you have a much more complex test with many more types of signal that need to be input, a DL850 would be a choice for you. Of course, the DL350 can accept most of those modules, but it means you would have to swap them as you go. We expect the usage model of a DL350 to be fairly well configured, I think. It will be people who have a very clear idea of the test and the number of channels they want. DL850, of course, provides more flexibility by having more channels available. We highlight here the difference in memory capability. They both, of course, provide extensive analysis. We have described some of the capability that DL850 offers in terms of real-time maths, which uses a separate DSP, digital signal processor, and dual capture. Of course, that leads on to the sort of the main application base of the product. We can see here that, of course, key attribute of the DL350 is the ability to have its 3-hour rechargeable battery for DC power, which means you would essentially have a very reliable method of making sure your data is captured when you need to capture it for. I'm conscious of the time now because we're running up to the hour, so I will probably wrap it up from this point. We have got some use cases for these products, which we will happily send to you. I don't know what questions we've had asked during this session, but we will respond to those. We will also, let me just go to the last slide. What we'll also do is offer you the features and benefits flyers. For these products, we not only have brochures, of course, which are extensive and multi-page, but we've also prepared some overviews of the products which are for easier reading, which are just 2 pages, which we call features and benefits. If you have more questions for us beyond the ones that you posted during the session, please address it to tmi@nl.yokogawa.com. That we will collect those and respond to those as soon as we can, of course. And of course, if you have any other requests, please also contact us to do that. So just to finish then, thank you very much for attending today, and we look forward to solving your complex measurement tasks in the future.
Thank you, Clive. I wanted to just say still thank you from my side as well. You will be receiving a follow-up email from us on this webinar still today, as already mentioned, including the recording. And I have been receiving few specific questions on this webinar, so we will address those questions also in the follow-up email. Thank you so much for your attendance, and I wish you all a nice day. Bye-bye.